So where we stopped yesterday was actually the way you design keys and everything, right? So where we stopped yesterday was how you design the keys. Hey Venkat, Joy, thanks for joining. So that is where, before I start designing the keys, before we start designing the keys, let's talk about the three basic operations. Actually, there are more operations in HBase than three. First is the get, second is the put, third is the scan, fourth is the increment, and fifth is the batch. These are the 5 operations in HBase. Get is pretty straightforward. You have a table, you do a get on it, and you pass the row key to it. You can pass filters, you can pass, what column families or columns you're looking for, you can pass how many versions you need. If you don't pass any of this, obvious things are assumed. If you don't pass the version, that means you're looking for the latest version. Column families, if you don't pass column families or column qualifier, then it's assumed that you're looking for everything. That's how you do a get. Put is table.put, row key, and then definition of everything, like we were talking about. For a value v1, it's the key 1, column family cf1, column qualifier cq1, time t1. This whole thing has to be defined for a value. So for a row key r1, key k1, you will have the column family, column qualifier, the timestamp, and v1. If you don't provide the timestamp, the system.milli timestamp or current timestamp is used in HBase. So HBase node receiving the data, the HBase node which is receiving the data will take the milli timestamp on that system and use that for purpose of timestamping. If you provide your own timestamp, yeah, it's going to use that. But at the very least, you have to provide these and then the value. Just a quick word about all of these operations. Everything in HBase is a byte array. Everything in HBase is stored as a byte array. Okay? So whether it's the value, whether it's the column family, the column qualifier, the key, everything is stored as a byte array. What this allows you to do is to interpret the data at the time of read in your own fashion. So there is no strict data types here at all. There's a good thing and a bad thing. It's a good thing mostly, bad thing very rarely. Bad thing is, yeah, it's a little bit more work on your side, on the read side, to convert it into the appropriate data type which you want to use it as. So that's bytes, so that's the put, right? Scan essentially almost looks like a get, except that there is an additional start row and a stop row which you can provide. You can provide scan from 1 to 9, for example. Okay? So scan works like that. Scan is almost, it's everything which we said about get is true for a scan, except that scan has an additional start row key and stop row key, essentially. If you don't mention start row key, it's going to assume you're going to start from the beginning of the data set. If you do not specify the stop row key, it will assume that you're going to go from the start row key all the way to the end. If you specify start and stop, stop is not inclusive, start is inclusive. The value of the start key is inclusive in your scan. The value of the stop is not inclusive in your scan. Okay, so that is scan. Increment is basically if you have a particular CF1, CQ1 and value 1, assuming that this byter is a number, meaning it's a long int or a whatever, it is just going to look up that number on the HBase node itself. There's no round trip involved to the client here. It will look up that number on the HBase node itself and increment it by 1 over there and store it. So there is no round tripping per se. You're saving on the round trip back to the client. So that's your increment part, right? And then finally is batch. Okay, so let's talk a little bit about batch. The last operation is batch. Actually, I would like to talk to you about scan and batch a little more. Okay. So before I go there, let's talk about how a read actually happens when you have HBase. Let's talk about the anatomy of a get operation. How does a get operation on HBase happen? So let's say I am trying to look up the value of K1, key K1. How is the thing happening? Okay. So on this side, let's say there is this HDFS layer. Within HDFS, there is a block of 64 MB size, data size, stored somewhere. HDFS 64 MB, 64 MB, 64 MB, which is housing the same data. Assuming that we are respecting the data locality principles, wherever this block resides, there is a region server which is serving a region which is corresponding to the 64 MB block size. This region server is serving that same region. And let us say I come looking for K1, which happens to be in this block. So what is happening internally within HBase is that from a read perspective, there is something called a block cache. And this is the actual, what do you call it, let's say this is the actual file, H file, which is storing the data. Now H file is basically a sequence file, and it is a sorted sequence file, basically. The data in here is always kept in a sorted fashion. What happens is, on this H file, there is an additional data structure which is basically sort of an index into this, and it says, well, the value 10 is byte offset so and so, value 20 is byte offset so and so, value 30 is byte offset so and so, value 40 is byte offset so and so, value 50 is byte offset so and so, so and so. So this is a pretty small, basically a block descriptor which is always stored in memory by the region server for that region. Okay, it's not huge. It's just okay. So what this, when you come looking for key K1 is bounced in this particular thing. Okay, first thing which happens is, let's say you come looking for K1 and the K1 is inquired in the block cache. If it is found in the block cache, it is returned to you from there itself. Block cache is a cache, in memory cache of all the all the records which you're looking for. If for whatever reason you're not able to get that data, then HBase looks at this particular thing, says, okay, he's looking for K1. He finds the byte offset of K1 is found. That particular thing is taken, it's loaded into the block cache, and from the block cache data is served to you. So this is the anatomy of a read operation, a get operation. Any questions?
Which file is it? Column family level or at a full level?
Very good question. So these files are at a column family level. So if your table has 3 column families, you'll have potentially 3 files and more by the way. So you have CF1, CF2, CF3. These will have their own individual H files. Within CF1, for the amount of data, you may have multiple H files. H file 1, H file 2, H file 3. Okay? So this is how the read operation works. So now, remember in HDFS, in the HDFS side, we went through FS input stream and FS output stream, and we talked about at length what is seekable and what is not seekable, you know, and all that. Did we talk about it or no?
I don't remember.
Yeah, we talked about FS input stream, and we talked about how, you know, name node is consulted and all that, and how do you resync yourself to a particular location in your file by, you know, starting from the byte offset from the beginning and then calculating from the byte offset from the beginning that you need to skip these many data blocks to reach your own thing. And that's how sort of a random IO is conducted. So if you notice, all of these things happen at a pretty fast pace because of the introduction of the sorted sequence file being kept, right? Now, since this is HDFS, there is nothing stopping you from opening that same region somewhere else. It's not like you have to open that region on that same server. You don't need to. A region can be served out of a different region server. Okay? Does that make sense?
Yeah.
Any questions?
One question. I mean, the block descriptor, right? It has the row key and the byte offset.
Byte offset.
Yeah, a row key and byte offset, right?
Right. Now, I don't want to go into too much detail over there, right? And that's all internal. I can probably give you some more documentation around that. But yeah, what's your question?
The question was that it contains the row key and corresponding byte offset for each row key. Is that correct?
Yeah. Yep.
I have one question. We have a Hadoop cluster with 10 nodes, and we have 10 regions, for example, and we have a key range for HBase. Are these key ranges statically assigned, meaning that 1 to 10 is going to one region, 2 to 20 is going to other region?
I can barely hear you.
Oh. If we have a multi-node Hadoop cluster,
right,
and we have region servers, multiple region servers running, and the key range of a HBase, for example, we have a key range of 1 to 100, and there are 10 servers. Is the division or the assignment of the key range to a specific region, like region server, is is between 1 to 10 is going to one region server, 11 to 20 is going to other one, so forth. And if one region server dies or that hardware node dies, there won't be any shuffling of other regions again, right? So they just need to have another node come up, physical node, and only that region will be assigned to that. There won't be reshuffling of the region, the key ranges.
There is no reshuffling of the keys which are tied to a region, but that region can be opened up on a different region server. Okay. Number one. Number two is, I'll come to the right philosophy on the right path. I'll give you an anatomy of a write operation also, just the way I gave it for the read operation. I'll give it to you for a write operation also. So when we get there, we'll see that. Essentially, there are two distinct concepts: region and region server. Region server is the server dishing out the region. Region server is the actual process which is running, while region is, look at it more like a file, that I have a file and this file needs to be served by a process. Now, by virtue of that file being on HDFS, you can literally start region server anywhere without respecting the data locality principle. You can start it anywhere and it will be able to open up and get to the file, the region which you want to get at.
Okay, perfect. Yeah, okay, got it.
Okay?
Yeah.
Any more questions on the read path?
No. One, you mentioned that increment operation is not that important compared to the other two, batch and the one scan. Increment you mentioned, once you are in the region, it will increment by one. What exactly is that? Because you mentioned everything is a byte array. So key is also byte array. There's no type associated to that. What is increment one means there?
I will come to that in a few when we go. We're going to cover the anatomy of a get operation, a put operation, and then I will explain the significance of byte arrays after that. Okay? So, that's how these things on the get operation works, right? Now, let me pose a question to you guys. You understand how this whole thing works now. What can potentially increase or decrease the speed of your get operations here? So let's say I have one get operation at hand. What can increase or decrease the speed of that get operation?
The
Block
filters.
cache.
Block cache, yep.
Okay, very good. So if I have a gigantic block cache, I can almost cache the 1 GB file. Let's say my region size is 1 GB, for example. The region size is 1 GB, for example. I can cache the whole 1 GB over here if I have a gigantic block cache. So I may take a hit of one time and then I will never take a hit of IO. What other things?
With size of H file, that's to a peak, the larger it is, it has an index.
The size of what?
H file.
The size of H file. Do you think it will play a big role?
Only one thing.
I'm not sequentially scanning the file at all.
Right. Yeah. You can see. Yeah,
it is this guy through which I'm going to this guy.
Right. That's true. So that shouldn't matter. You can just see.
Right.
Exactly.
The second principle which can cause a problem is, how are you accessing the H file? You're accessing it through a data node? You're accessing it through the data node, right?
Yes.
Right.
Because this is HDFS, right? The files are stored on HDFS. Whenever you're saying HDFS, that means you're talking about a data node, right? Correct?
Yeah.
Correct.
So if it is not local, it's a network round trip. So that
Right.
can affect your get speed, correct?
Correct.
Mm-hmm.
If it is local, if the H file is local, can't you not short circuit this? If the H file is local to the region server, meaning it's on the same Unix box as where the region server is running, then potentially you can short circuit this. You can say, I don't want to go through this abstraction layer called data node because I know the content I'm looking for is on the box where I'm sitting at. So the second thing which is the whole thing about local or remote and all that, and that this is called a read short circuit. This also governs what kind of speed you can achieve for your get operations. So coming back to my original thing, if I have a get operation, not many, a lot of get operations, right? A lot of get operations, I will come to that in a second, okay? So that's how the get operation works at this level. Any questions thus far? None, right? Let's look at this from a client's perspective. Anatomy of a get operation from a client's perspective. So the client is, here is the client. And he has got a key K1 and he's looking for key K1. And there are 1,000 node cluster, let's say. There's a 1,000 node RS1 through RS. Let's make it 100 node cluster. How does he know where is K1? How does he know which region server is K1 on?
You mentioned HMaster.
Right. So what he does is there is an abstraction layer here called the client. Okay. This guy's first job is go to the zookeeper and ask the zookeeper, give me the name of the HMaster. So one of these region servers actually maybe the HMaster. Now when HMaster is HMaster, it doesn't behave like a region. It doesn't behave like a region server, right? So his only job is to store this file called meta. This file contains, like it's basically a file which contains list of tables, the ranges of keys for that table, and which region server is serving the particular range of keys of that table. So this is your first operation. Your second operation is this. And from the HMaster, you get the meta information. From the meta information, you get for this table, there are the ranges of keys. And therefore, it comes to know that I need to go to this guy for key K1. So let me ask you this now. Is this operation 1, 2, 3, 4 performed on every read?
No.
Not necessary.
Okay. So can you please say more?
So let's say if it is like second K1, I mean the client already knows which region server to go. So he
K2, right? So I'm looking for K2 and I've done a read for K1.
In that case, step 1 is omitted because he knows the HMaster. He'll go to perform 2, 3, and 5.
Right. Right. And then do you need to perform 2?
Depends. I mean, in the previous call.
You don't need to, basically. So because the H master has given you a range of keys,
Oh, okay. Okay.
so you don't need to perform K2. However, if there is a region split happening on this side, right? If there is a region split happening on this side, then this guy's cache has to be invalidated. Correct? Correct?
Correct.
If I'm opening up a new region because of some size restrictions or whatever, I can't let my regions grow beyond a certain level. So there is a region split which may happen. So any existing running client, his inventory of ranges needs to be invalidated, and therefore as a result of that invalidation, it has to pull this up again. But the point is this, that I just wanted you guys to appreciate that it's not 3 networked round trips to do something. It may be 3 in one case, but after that it's not. In one case it may be 3, but after that it's not. Any questions on this? Any questions on this?
No.
So
Okay,
step 1
good.
is always because
Yeah.
Zookeeper is the only way we can go, right? So Zookeeper is the first guy we will hit to.
Yes, it's going to be the first guy to hit, but you're not going to hit him every time. Same thing with the H master. You're not going to hit him every time, but you will hit the region server every time.
Okay.
Okay?
So, okay.
Now, all of these 1, 2, and 3 are basically RPC calls. RPC calls by this guy. And RPC calls are always expensive. Just know that. Just keep in mind that RPC call is expensive. Why am I telling this? Is, when I say batch versus scan versus get versus put, this is very important. This fundamental concept of RPC is pretty important for you to respect and keep in mind. So all of this stuff is done via RPC calls. And by the way, data is always kept in a sorted order. I've said that many number of times. The data is always kept in a sorted order. Now, sorted order means that it's not like that, it may so happen that RS1 is handling 1 through 100, RS2 is handling 1000 to 1010, and RS3 is handling 100, 1 to 200. But it is sorted, right? It's not that region server assignment names should also be in a sorted fashion. There is no ordering of region servers. Region servers can be intermixed. But data overall is kept in a sorted fashion. And this guy is telling you where to get what key, etc. Make sense? So this is an anatomy of a read within a region server and within a cluster. Okay? If this guy goes down, for whatever reason, number 2 goes down, then the H master can be made highly available on a different node. Okay? Now let's go back to the cap theorem for a second, okay? This is a distributed database. HBase is a distributed database. What of the cap theorem are we always sacrificing?
partition problem?
We are always sacrificing availability because this guy is a single point of failure. If this guy is down, you are down. Make sense?
Yes.
Now you can make this HMaster highly available on a different node, and if this goes down, you will have a temporary hiccup on your client side, and this HMaster will publish its information to the zookeeper. You will perform one, you will get a new address for the HMaster. You will get the new address for the HMaster. You're going to go to this guy, and from here you will perform the same operations. So you understand what role zookeeper is playing in the whole thing?
Yeah, DNS.
Yeah, that's it. Yeah.
Actually, it is doing a lot more. All these region servers, they actually report their status or health to the zookeeper. And the zookeeper is actual service, is actually the service, in fact, HMaster also. How would the cluster know that your HMaster is down? It's the zookeeper who is managing all that. He's more like a doctor for your cluster. He keeps tracking the health of your cluster. He sees what region servers are up or down. If they are up or down, lets the corresponding entity, the HMaster, to remove him or open a new region server, etc. for it. So all of this is managed through the zookeeper. So while it acts as a DNS, it's also acting as a health check system. Okay?
Okay.
So that's what it is. So that's the anatomy of a read. Now let's talk about anatomy of a write. Just like how we did a read at a cluster level, not within a region server. The same process is followed to do a write. At the end of the day, you identify a region server based on the range of keys, and you go to that region server and you want to insert in that. Any questions? Should I explain that part, or you are pretty clear on that? You contact zookeeper, contact HMaster, go to a node and do a put operations. Any questions on that?
No.
Okay. So now what happens inside the region server is what we're going to talk about, okay? So what happens inside the region server? On the read path, there was a block cache. On the read path, there was a block cache. On the write path, there is a mem store. So whenever you do a put or an increment, you actually do it on the mem store. All right. Now mem store, actually no, that's not how it is done. Okay. Whenever a put happens, this is step number 2. Step number 1 is you write it to a write ahead log file. The first thing which is done whenever a put happens is you write it to a write ahead log file. Write ahead log file is almost the same concept as your redo logs in your Oracle database or your DB2 or your SQL database is concerned. That you write your transaction out into a separate file. The uniqueness of this file is that this file is also resident on the HDFS. which allows the HBase master to recover a given set of transactions should there be a failure on a particular HDFS, on a particular region server. So for whatever reason a region server dies, if a region server dies, the fact that you have never lost the transactions which occurred on that region server by way of persisting it in an HDFS file allows another region server to read that write-ahead log file for that respective region and apply those changes to the necessary files on that region. So that's the purpose of write-ahead log file, WAL, write-ahead log file. It's also persisted into HDFS, by the way. So first is, whenever a put happens within a region server, you actually do a write-ahead log file entry. After that, you actually put it into memstore, and that's it. And you return back to the client saying, I acknowledge that things are okay. Whenever this memstore fills up to a particular size, for example 64 MB, then you flush the memstore into your H file, which is a persisted file on HDFS, and forget about the write-ahead log at all, totally. You actually, till that checkpoint where the memstore was flushed into H file, you invalidate that part and you say, okay, whatever has not been flushed to the memstore, start from those transactions in write-ahead log file. Okay? This process is independent of this process. 2 and 3 are independent of each other. Any questions? Any questions?
No, this is similar to how the name node in HDFS is handled, right?
This is similar to how what node?
When we create HDFS files and assign the last name node, how it has a
right. Now, keep in mind, HDFS is an append-only mode file system.
Hey, Pitpal, I was just wondering one thing. You said step 2 and 3 independent to each other, but if the memstore is getting over 64 MB, then only that step 3 will be happening. So
right.
How can it be independent to each other?
How they are independent? Because
yes.
Let's say you're doing 1,000 puts. Let's say you're doing 1,000 puts. Each put is 1 KB. It's bringing in 1 KB of block size. So 1,000 puts is how much? 1 MB? No, how much? 1,000 KBs, right? Which is 1 MB. Let us say that the flush is not happening at 64 MB but at 1 MB. So that means your 999 puts will return back just like that, and memstore is not flushed here, correct? When the last put comes, let's say you're doing 1,001 puts actually. So 1,001 put. When the last put comes, would you like to hold up that put until number 3 happens, or would you just say, okay, Mr. Number 2, number 2, I'll hold you up until I write this file out to H file, or would you let it return back?
Return back.
That's the thing. That is why I'm saying 2 and 3 are independent of each other.
Okay. So log file WAL, this is the number 1 step. It happens many times, and it happens only what is left over in the memstore.
No.
No.
The WAL file is the write-ahead log file, okay? The job of this particular file is to record every transaction coming through, okay? Now, this guy is in memory, okay? This guy is in memory. This right here is in memory. It's in the JVM. Let us say that JVM crashes for whatever reason. That means you would lose all the data which has been put into this mem store. Correct?
Yeah.
Where are you going to recover the data from?
WL file.
Yeah, so write-ahead log file would have a record of every transaction which is filling up this guy. And you will replay this write-ahead log file to repopulate memstore to this level again. Or you may actually take the write-ahead log file and apply it to an H file. Whatever you want to do, you can do. Okay? So you will repopulate it into the memstore, and then the memstore, when it fills up, it flushes it out. So that's the purpose of write-ahead log file. But let us say the JVM never crashed, and your memstore filled up to this level. It filled it up, and you did write it down into an H file. What should you do with all the entries in the write-ahead log file? What should you do with all the entries in the write-ahead log file?
Does it have
It
a
will
limit
go
to
to the main
log
store.
file?
Huh?
It will go to the main store once the main store will reach the 64 MB in the step 3.
Right, so 64 MB is filled up, and you're flushing it to the disk, meaning to the H file. What should happen to the corresponding log file entries for whatever has been flushed to the disk?
It will wipe out?
Yeah, you basically don't wipe it out, you discard it. You just say, hey, I'm keeping record of these transactions. I'm giving 1, 2, 3, 4, 5, 6, 100. Say, let's say at 100th entry in the write-ahead log file corresponds to when the flush happened. You will say, okay, you know what? Disregard, you don't wipe the file actually. You just say disregard anything before 100 because I just persisted everything into H file. So now what is unflushed onto the disk is 101. So write-ahead log file is basically a mechanism or a medium by which you are able to recover a failed, a failed JVM memstore or whatever. Okay. So what happens also? There is one more thing which happens in the memory is when this is to be flushed, a new memstore is opened and any new puts are put in here. So this is actually flushed in and then destroyed. So you create a new memstore in memory every time you want to flush. What this allows you to do is it does not hold or freeze your system because the memstore is full at that particular time. So you always create a new memstore whenever you reach the full state of this thing. Any questions?
Praveen.
Yes.
So, does the client writes into WL?
I mean, the region server writes WL. It's the region server. All of this thing is happening inside the region server.
Okay. And the second question is when the memstore or a H file is created, and I know, H files are stored on HDFS, and we know that you cannot insert any data in between. It's append-only file. So let's say if HBase, the data is always sorted. So if there is a data returned for a specific key which is supposed to be somewhere in between, so how the files on the HDFS are synced? Does anything happen, or HBase takes care of it while reading the data from different HBase?
So latter is true. The very good question you asked, right? Good question. Okay. Let's wipe this whole thing out. Any questions on this? I'm going into a different subject. The subject is that let's say at time t1, the question Praveen is asking is, at time t1, you received for a key k1 value v1. And at time t2, you received for the same key 1 value v2. But there is enough lag between t1 and t2 that this transaction went into file number 1 and this transaction went into file number 2. So his question is, how is HBase able to guarantee that the data is still sorted? That's his question. That is his question, really. Right? That's what you're asking, right?
Yes.
Okay. So K1 V1 and K1 V2. That's the question he's asking. And I will like to answer that after I'm done here. Any question on this guy? Okay, no questions, so I'll move on. So let's answer that question. Would you agree that a given state of memstore is always sorted?
Yes.
Would you also agree this is a columnar data store?
Yes.
Mm-hmm.
That means I'm not storing anything as a row, I'm storing it as a key value pair, where the key is K1, CF1, CQ1, and time T1. So whenever a memstore is flushed, a new H file or an append to an existing H file happens, correct? So whatever your block size is, your H file 1 and H file 2. So if a value goes into, after a flush, if it goes in here and then here, internally within H file 1 and H file 2, everything is sorted, correct?
Yes.
So H file 2 internally is kept sorted, H file 1 is internally kept sorted. So when somebody comes and does this, gets K1. When somebody comes looking for K1, both these files are read by HBase, and appropriate versions in the sorted file are picked up, which is V1 and V2, right? And depending on what he needs, V2 is presented to the guy. Does that answer your question?
Yeah.
The point is this, you don't write to existing files. Or you don't edit existing files, correct?
So
Yeah.
it is just the get operation who is going to make sure that the right value is returned.
Yeah, RIGHT, yes, right values are written. Okay. Now, there is a possibility of a problem here. The problem is if the speed at which you're writing data into this is high, that means the frequency of flushes are very high. That means you will create more number of files.
Mm-hmm.
That means at the time of get, you would have to keep these many number of files open. So therefore, HBase introduces the concept of compaction. Okay, you can't have 7 or 8 files open to do a get and then try to figure out, okay, out of this. So there is a concept of compaction open, which is called minor compaction, major compaction. Behind the scene, not at all affecting the client or whatever. What HBase does is, it takes these 7 files, as part of minor compaction, it takes these 7 files and reduces it to 3, for example. And it does that very periodically in HBase. How often does the minor compaction kick in? It's totally left up to HBase. And then as part of major compaction, it may take the existing number of files at that time, which may be 3 or 7 or 10, and does a whole scrub of this thing and produces 1 file per column family. Right? As part of that, the min version numbers, the max version numbers, etc., etc. We'll go through that also in a few. We will discuss the min, max version numbers, etc. of these key values which are kept in the in the file. Right? So this is happening at this thing level. Does that answer your question? Major minor compaction is what handles the growth of the number of H files.
Yes.
Yeah. So Preetpal, one question about compaction. So you explained like just the purpose is not to have those many files opened in the open state. It has been compacted into a one H file.
Correct. That's major compaction, by the way.
Just to reduce the I/O.
Yeah.
Okay.
Just to reduce the I/O and the disk space.
So,
now there is one more thing you need to keep in mind. That a given region is defined by a size. Okay? A given region is defined by a size. That means you're saying a given region will host 1 GB of data or 2 GB of data or whatever. What is 1 GB, 2 GB? It's the size of these files. Collectively, taken collectively. Whenever the collective size of the file, and whenever you say collective size of the file, it also means it's also playing into the argument of the number of files, right? I mean, you can safely say that the collective size of the file is also equivalent to the number of files. So at a cluster level, you're opening up new regions whenever you hit a critical threshold higher than the 1 GB size of this thing. So you open up new, you do a region splitting, and I will explain region splitting also in a few, right? You open up new regions whenever you hit that 1 GB size. So again, from that angle, you are again restricting the amount of files open by you're restricting the number of files open. You'll never have a situation where you'll have hundreds of files open, because if there are hundreds of files open, that means that much amount of data is also there, which means you have crossed the boundary of the region sizes. Make sense?
Yes.
Okay. So wonderful. So HBase has many of these safeguards which automatically takes care of all of these things. Any questions? No questions, then I'll move further, okay?
Recall Praveen, during major or minor compaction, when this multiple H files are merged into one H file, I presume the data is again sorted and then stored into the output H file.
Yes, sir. What did I say? The first stipulation is a given sequence file, which is an H file, is always kept in a sorted order. Okay, so I think I was able to explain major compaction, minor compaction, mem store, write ahead log file, how failure and all of these things are handled, etc. So I can also explain in the same breath, or I would like you to explain it to me, is whenever you hit that 1 GB file, the region size, meaning the size of the region is 1 GB now. Obviously, HBase will say, you know what, let's split that region. How is that splitting happening? How is that splitting happening?
On the keys.
Right. So let's say you're trying to do a put here. And this put will result in the size of the region to go above 1 GB. So what's going to happen is that same key which is coming in, see, all the regions, they have a start key K0 and a, start key KS and an end key KE. So if you did a put just now, which is for K1, if you did a put K1 here, which results in the size of the region to be larger than what it is, what's going to happen is this will become region R1, this will become region R2. Is anything being moved around as part of this process?
No, the meta file should be updated, right?
Yeah, one is meta.meta file needs to be updated, which is the job of the H master. What other things need to happen? Do you need to copy any file?
I don't think.
Yeah. So what happens is, whenever this split happens, the first thing you do is, regardless of whatever the size of the mem store is, you flush it. You flush the size, the total mem store, and your H file is persisted on the disk. Then you open up the new region and you give this guy its own mem store, this guy its own mem store, and say, okay, go ahead, have fun. Make sense?
Yeah.
Now, these files, they don't need to be split at all. They don't need to be. The only stipulation is that the files are kept sorted. That's it. These files do not need to be split. Nothing stops you from reading an existing file from region R1 and region R2. And any new updates will be into a new H file, by the way. Sorry, I shouldn't use the word update, inserts. Will always be into a new H file. So in this case, region R2 will have its own H file, region R1 will have its own H file. This H file will never contain any key between this and this. This H file will never contain any key between this and this. So that's how, this is the phenomenon of region splitting. Now, at the time of region splitting, yes, there is a pause. There's a pause for the client. Client has to hold on for a few seconds or a few milliseconds, or whatever time it takes. The idea is, first you flush the mem store, then you split the region, Then you inform the master that there was a region split because of the size thing. Kindly update your metadata. Then you acknowledge the put to the client and also tell him to invalidate his cache. And he picks up new region information from the zookeeper, the H master, and then goes on his own way.
Would there ever be a case where the data associated with one key exceeds the region limit?
Data associated with one region? What?
With one key exceeds one region limit. Let's say in the example we're talking about 1 gigabyte limit. We're talking so would there be a case that one key has more data that could fit into one region?
No, a key is always handled by the same region. You cannot have a portion of the data handled by one region and another portion by another region. No. Things work at a key level. You cannot have key K1, V1 on being in region number 1 and key K1, V2 being on region number 2. Nope. Not possible. In fact, it's not. I mean, when you split the region, everything related to, see, because there is no concept of an update here. See, this whole region notion, right, is allowing at the read time, this guy is capable of opening H file 1, is capable of opening H file 1 and reading data from there. And this guy is also capable of writing, by the way, this guy is writing data to its own region file, H file. It's not writing to this guy. So yeah, I mean, that means that I don't have to have a situation where a key needs to be handled by two regions. Never. It's going to defeat the philosophy of HBase. If that happens, there is no HBase.
Right. So what happens if the key has so much data associated with it? It's because of the skew in the data. So much data that won't fit in one region.
You're saying a key K1 has more than 1 GB of data?
Yeah. What we define as a limit for the region has more data.
Well, you have to then go change the region. 1 GB becomes 10 GB.
Okay.
Otherwise, it will be always continuously splitting. It will continuously split. You'll almost end up in an infinite loop. Okay? Wonderful. Any questions? So by virtue of me doing this, I have explained what write path looks like. I have explained major minor compaction. And I have, what else have I done? I've also talked about region splitting on the right side, on the right path, because of these three things, right path. Now a question to you guys. What in your opinion dictates the speed of a write? I have two questions actually. First question is, what's the harm or benefit of turning off write ahead log? And my second question is what I just asked.
I mean, you might end up losing data in case there the machine or node crashes.
Okay.
But it might improve your write performance.
Very good.
And I think also your mem store size will have some, I mean, not necessarily, I mean, if it is independent, will it help your write speeds if you have a more mem store?
I didn't understand your question.
No, will mem store have any play in write speed?
Absolutely. But it can degrade the performance also.
Mm-hmm.
What if I have a 1 GB mem store?
I don't think it will impact, right, Prishpal, because memstore anyways works independently. Even if it has to get flushed, a new memstore is created. So
Right. But it's, yes, they are decoupled. The put on step number 2 and this flush are decoupled. But still, if I have a mem store of size 1 GB, that means at a given point of time, I will be flushing 1 GB of data to the disk. At that time, although 2 and 3 are decoupled, but they are running on the same hardware, same CPU, same RAM, same disk, right? Same network. Correct?
Correct.
So it may have a CPU, a box impact, not really the decoupling impact. So yeah, mem stores play a significant role in the flushing, and typically the larger the mem store, that will guarantee what we just talked about. Make sense?
Correct.
Okay. What other things can potentially impact your performance? On the right side.
You write to the write-ahead log.
Yeah, we discussed that. Pramod talked about it, and he said, I can turn off write-ahead logs with a crisp understanding that if any failure happens, then if memstore is ever corrupted or it goes away or whatever, I will lose data. But maybe my use case may allow me to do that. Maybe when a region server fails and that failure is reported back, well, no, not really. 99% of the time you cannot walk away from turning off write-ahead log files and still expect zero data loss. So yeah, broadly those are the factors which are contributory factors towards the speed of your write. Another factor is, what is your HDFS really doing? At the end of the day, data needs to be persisted on HDFS. If your HDFS speeds are not good enough, if you haven't opened up your HDFS a lot for write performance or whatever, then it's again going to suffer. So it's that, my friend, is the story of HBase. I mean, that's the story of HBase. From a memory perspective, we discussed two distinct data structures. One was the block cache, the other is the mem store. Block cache plays a role on the read side, mem store plays a role on the write side. By default, when you are tweaking your HBase settings or whatnot, these two together, by default, are fixed at 70% of the total JVM heap size. Okay? Mem stores are kept at 40% of the JVM heap size, and block caches, if you don't tweak it, if you don't change any of this, they are kept at 30% of the total JVM heap size. Okay? Any questions on this one? Okay, so let's move on. Okay? We discussed, okay, let's look at it from a client perspective. I'm the client. I've got 1,000 rows to write, or rather 1,000 puts to write, sorry. Why am I using the word rows? There is no word called row here. Okay? By the way, what is the concept of row here? The concept of row here is a key K1 and all associated information to it. So the row here is K1 and all associated information. The row is not a single line, because in here a given column qualifier CQ1 may have value V1, V2, V3, and then second guy has V4, V5, V6, V7, V8. What is a row? This is a row. Everything taken together is a row. In HBase, this is the row. Really, that's the concept of a row. So let's say I have 1,000 puts. Let's say I have 1,000 puts to make. And this is my HBase cluster. I'm going to call it an HBase cluster, really. If I leave it to just the same way it is, how many RPC calls will I need to make to do 1,000 puts? Answers.
Maybe 2, if there's some batch update.
I will make 1,000 RPC calls to insert. So there are 1,000 network round trips. So how can I minimize it? I can minimize it by taking that 1,000 and batching it up. I can say 1,000 ports, batch it up, and send it in one shot. But is this statement true? One shot statement true?
Yes.
No.
No.
Why?
Yeah, because of the keys.
No, not because of the keys. Why no?
Because the asset integrity is still at the key level.
Huh?
Transaction integrity is still at the key level, right? Even though you're sending 1,000, you're just batching up 1,000 independent puts.
No, I think the answer is no, but the logic is wrong. The logic is you have to make a RPC call per region server. Does that make sense?
Yes.
Yes.
Because the client is independently talking to individual region servers, right? You don't know whether all these 1,000 will go here, or some of them will go here, some of them will go here, some of them will go here. You don't know that. Right?
Right.
So there is this batch concept of there's the concept of batch, which definitely is going to reduce it from 1,000 RPC, but it will not be one shot. The client is going to individually write all the data to the associated this thing. So, I mean, to the associated region server. So batching is a concept where you don't do 1000 RPC calls, but you do lesser number of RPC calls. Now this is a client-side function really. Client will decide, if I need to do 3, 4, 5, 6, depending on how the data is distributed, all that. Keys need to be sorted, and then when a thing is opened up, then you actually do a write or whatever. So there is a client-side batch size, which is very important. So if the client-side batch size is large, for example, it is 1000. Then, of course, this 1000 puts have to be sorted, because by sorting you will achieve this region distribution or whatever. So this also plays into performance, the batch size on the client side. Make sense? Does that make sense?
Yes.
What I am trying to do, guys, is to give you the anatomy of everything so that you don't need to by heart anything. You understand the science behind the whole thing. Okay?
Mm-hmm.
Okay. So this is called the batch concept. So when you're trying to do a series of puts and you want to reduce the number of RPC calls, then you have the batch concept. Okay? Similar to the batch concept on the put side, there is a batch concept on the read side, on the get side. Right? Now, this is your HBase cluster. Now, let's talk about scan, okay? Let's talk a little more about scan, the scan operation. What is the scan operation? I need something from key KS to key KE. I need something from key KE. Now, this is called a scan operation, from key AKS to key KE. If I do not mention KS, then it's assumed that you're doing from the beginning of you're doing it from the beginning of the table to the end of the table, to the KE. If I do it from KE, sorry, if I mention KS but not KE, I'm doing it at the end. If I don't mention both these, I'm doing from the start of the table to the end of the table. That's the scan I'm doing. Make sense?
Mm-hmm.
So now, the data I get back can be one row. What is a row? A key and its associated information. For RPC call, or I can say the scanner cache size, the batching concept on the scan side. See, get does not have a batch size concept. A get will get all the data in one RPC call. It will do it in one RPC call. But on the scanner side, on the scanner side, potentially if there are millions of records, millions of rows to be extracted from HBase, you will make 1 million RPC calls. How can you reduce it? The way you can reduce it is on the cluster side, you can say scanner cache size is equal to 10, which means on every RPC call, return 10 rows. That's what is being returned back to the client. Any questions? Any questions here?
No.
Okay. Wonderful. So do you understand what scan also is doing? Scan is basically saying scan from KS to KE. Now that KS to KE may spawn or may span many different regions. It may span 5 regions, for example. So the client will issue a scan to individual regions. Make sense?
Yes.
Okay, wonderful. So this is what scans are. So I have discussed get with you. I have discussed put with you. As part of get and put, I discussed what are the read and write paths into HBase. I have discussed scan with you. I haven't discussed batch with you. So the last thing which is remaining is increment. Last thing which is remaining is increment. Now, before we talk about increment, I want to spend a few minutes talking about bytes. What is a byte? What is a byte?
Collection of bits.
Huh?
Bits.
Bit.
Byte is a bit.
No, sequence of bits.
A sequence of bits. Very good. Okay. Can anybody say more?
Binary information.
All right. So you are understanding it to be a binary information, right? So the byte we are talking about here is basically a Java byte. What is a Java byte? The Java byte is, how you define a byte in Java is, it's a 8-bit signed 2's complement integer. Okay? Make sense?
Yes.
I would like to represent a byte as this. Well, I personally, I don't know how many F's go in there. 00 through FFFF. And then there is this whole shifting operation, right? At a bit level. Well, I will admit that I'm not very good at bitwise operators, such as AND and shifting and all that, right? Essentially, when I'm talking about increments, what I want to say is, would you consider this as an increment? Is this an increment?
Yeah.
Is this an increment?
Yes.
Is this an increment?
Yes.
Yeah.
So these operations are bitwise and or shift basically operations. You know, I would have to pick up a textbook and learn this and then explain it to you. If you want, I can do it by next class. I will get more information on this, but what I was trying to explain here is that information in HBase is stored in this form. It's a 2's complement integer, and it is stored as such in HBase, like that. Okay? That's what I wanted to tell you. And it's a hexadecimal representation. Whenever I say an increment, it's a bitwise AND or shift of the existing bytes the sequence of bits in HBase. So I can do a bitwise shift or AND of this thing and achieve the next higher number. That's how increments work in HBase. Did that make sense or no? Or I can come back in our next class and talk a little more about it.
No, I think the question I had before was because I was assuming it's a plain bit sequence, right? Just a bit, but now the fact that you mentioned it has a type associated with an integer, truth complement integer, yes, then increment. There's a logical operation, there's an operation called increment once there's a type truth complement integer. You're just doing it over there.
Right. I could barely hear what you said in there, honestly. But from whatever you're saying that I understood what we are talking about.
Right. So I was thinking if there's no type associated with that, so there's no way to tell that 0000 comes before 0001. Now we're telling that 0001 is after 000 because we assigned a type to that called integer.
Right. So basically, the way you should understand increment is, regardless of the data type, it's a bitwise operation. Bitwise operation, yes.
Okay.
Right. So if you were really storing a string in there and not a number, it's still going to increment it as though it's a string. Okay. Now, if you take Unicode character set, and you look at A, and if you do a bitwise shift, the Unicode number for A is +1 of, B is +1 of A, right?
Right.
So it still holds true, correct?
Yeah.
So you actually can increment a string also using the increment function. And numbers they always work the same way.
Okay.
Numbers, they always work the same way. Numbers work the way I was showing you just now. There's 000, 001, then 0010, then 0011. All of this is bitwise operations. So I think what this would be is it would be a bitwise left shift and then add 1 to it. You see this right here? I think I found it. I don't need to go and read my book. So what's going to happen here is you will take this base number and you will shift it left one time. So your base number, when you shift it left by 1, it is still 000. And then you will add 1 to it. So 1, it becomes 0001. Then again what you will do is you will shift it left by 1. So now your new number, this number becomes 0010, and then you will add 1 to it. No, hold on 1 second. 0000. Shift left 1, so the new number is 0000, and then you add 1 to it. So your new number is 001. The next number is 2, which means
I think is the AND operation, right? Here it will be AND operation when we shift and then we AND with 1.
Yeah. This is.
That's what I vaguely remember.
Yeah, I mean, how's an. Yeah. You're right. Yeah, that's the half adder and full adder. The full adder and the half adder. That's the concept. How do you add 1 to something? You add 1 to something by full adder. So the sum is going to be, if I'm doing a sum of this with this 1 plus 1, the output should look like this. So the sum and carry. Sum is a bitwise and a carry is what? Bitwise XOR. A bitwise XOR, I think so. Because this is a carry, right?
Yeah.
Okay, sorry, this is sidetracking the whole subject. This is not the purpose of this meeting. We are not teaching each other how to do binary adds and binary this thing. Although I can do it, but I'll have to go refresh. Prepare for it. So any questions on increment operation? How is increment happening? The increment operations function is not to make a round trip. This is a HBase cluster, right? The increment operation is not that you will bring the value here, add 1 to it, and then put it back here. No, that's not what increment is. Increment is this guy is going to issue a command called increment. And this is going to go here. Whatever the value here is, it will be added plus 1 over here itself. And that's it persisted here. Make sense?
Can you explain that again?
Okay. So let's say there is a value 10. I want to increment it by 1. In an Oracle database, what do you do? In Oracle database, this is a database, DB, you will read the value. You will read 10 here. So once the 10 is read, then this guy is going to say add 1 to it. So it will be 11. He'll send the value 11 back to the database. Correct?
Correct.
So how many round trips?
2.
2 trips for example here, right? Now in HBase, you have a provision where you have a value 10 in here and somebody issues the command incr. No value has been sent to the client. Client is not making 10 into 11. What's happening here is within the database, this 10 is being converted into 11 and put back in right here. So think of an increment as a put on the region server side, not on the client side. Make sense?
Okay. And that will change the value, right?
Yeah, it will change the value. It will not change the value. It will insert a new put.
New put.
So I guess we have covered all the basic concepts of HBase. Are you guys comfortable with HBase now?
Yes.
Yeah.
Okay. So it is time for us to start playing around with HBase a little bit, okay? So let's start playing around a little bit with HBase, and this is what I would like you guys to do. Now I will talk to you about how do you log into HBase and those kind of things, okay? I think I'll spend 5 minutes and then we'll pick it up in our next session. Okay, so we'll pick it up in our next session. We'll spend 5 minutes here so that if somebody feels like playing around on their own, they are fully capable of doing that. So, how do you log into HBase? The way you log into HBase, some basic commands on HBase is you use HBase shell. So this is how you log into HBase. This is your prompt for HBase shell. It's written in Ruby, so you can actually write Ruby scripts and do whatever you want to do. Now, I can scan anything in here. For example, I talked about the fact that there is a meta. So this is your meta. So your meta is holding region information just like I explained. These are the region informations. It's ATC. Start key is empty. Start key is empty here. And end key is this. This is the end key. No, sorry. This is the region ID. Okay? This is the region ID, which is a hash of something which becomes the region. So this is the table ATC log. This is the region ID for that. A region ID or a region of this particular table. Similarly, this is another region, this is another region, and this is another region, so on and so forth. These are many such regions. So the region is, the start key is blank, which means all values lower than this value come into this region. Okay? Make sense? This is the region ID. You have the start key as blank, end key as this thing, encoded is this, right? Similarly, you have, this is the second region of this particular table, ATC log. And the start key is this, is the start key, and end key, this is the end key. Right, of course, that is a byte array, by the way. It's a byte encoded byte array. Okay? And I can actually take this and I can do this. Columns. So I am filtering. I'm saying I only want to look at this column. Oh, sorry. Right, so these are the region infos, right? So I've got a region info here, which is the start key is blank, end key is this. This is 02, right? This becomes the start key of the next region. The end key is 5 KB. 5 KB becomes the start of this region. 5 KB becomes the start of this region. End region is EA. EA becomes the start of the next region, and the end key is blank, which means go to the end. What is it telling you? How many regions does this table have? Huh? Hello?
4.
Very good. So this table has 4 regions. So possibly this table is storing 4 gigs of data. Possibly. Okay? So that's how things work. Now I can do something like this. I can say ATC log, and I can say limit 1, meaning give me only 1 row. So this is the key value pairs which you will see. Now whatever we have been talking about, this is the row key, this is the column E, this is the name of the column, this is the value of that column, and this is the timestamp, right? Similarly, this is the column qualifier, this is the column family E, and this is the value. Similarly, this is a column qualifier, this is a column family, this is the value, so on and so forth. Make sense? Now, what if I wanted to see the value here? What if I wanted to do a get on a particular thing? So give me 1 second, and I'll do that for you. So this is how you formulate a key, right? So I'm going to formulate a key. Shift, Control Shift N, no. All the way to the end. Right? I can put it in single quotes, and I can say, I can take this value, and I can say this. I can say get ATC log, comma, 10. No, nothing found. So must have done something wrong. This is your key. Okay? This is your key. Right? Now this is a byte array. I think if I do this, it should come back. No, I didn't like it. Maybe if I do double quotes, it will come back. Yep. So the difference between a single quote and a double quote, the difference between a single quote and a double quote is, whenever you say single quote, it's going to treat this as a string and convert it into its own byte array form and then use that to do the query. When I put a double quote, it's telling the shell prompt that please do not interpret this, meaning please don't convert it into byte array. It is byte array, so just use whatever I'm giving to you. And this is, when I say this, when I say get on the ATC log for a particular key. So this is the table name, this is the key. I get all these attributes. So the column name is E, this, that, all of these things. 15, 16, 17, 2, 1, 5, 7, 8, 9, 1 row sequence. So these are the various columns, right? So I can then say this. I can say, so if I want to select a particular column, I'll say this. I will say this. So it's going to give me the value of that particular column, which is -1. If I say this, no, if I say ITM timestamp, right? I can also say this. I can say, give me everything in this column family. It's only going to be I's. All right? Any questions, guys? Hello? I think I bored you guys to death. So this is the end of today's chapter, or today's conversation. We still didn't do a lot of row key design yet, so hopefully in our next class we'll be able to do some row key design. Okay? Any questions?
No.
Hey, Principal.
Yes, ma'am.
I actually need your help after the class or some point when you are free, just because my previous laptop has corrupted, so I had a new one. And whatever I built, like the, one point you gave us, the IP address and stuff like that, that is not working. So I need help in order to access the HBase and practice.
We'll do that. We will get together and do that. please let me know a good time when you would like to meet, and I will make arrangements to meet at that time.
I think you are pretty busy, so why don't you tell me when it is convenient for you?
Are you available anytime?
Yeah, I can do that just in order to set up the initial stage.
Okay. So if you are available anytime, we can do it.
Okay, so do let me know what time and we'll do that.
All right.
Okay, thank you.
Sure.
Pramod.
Yeah, Pramod.
Hey, when do you want to speak? Do you
give me an hour, and I will call you. Okay?
Okay. Yeah. Thanks.
All right. Thank you. So any questions, please shoot those questions. My assignment for you guys is to get very familiar with HBase shell. Okay? Please get onto your Unix boxes into your account, set up your access to HBase, and get familiar with HBase shell. Now, where am I going to find all the commands? You're going to get all the commands from Google. So Google is your best friend, and you can get all your information from there. What are the different commands on HBase shell? I think I can actually provide, one second, I think I can provide a web page which is pretty comprehensive with all the commands on HBase. HBase shell commands. Hold on, let me find that out. Okay. Yep, that's what it is. Yes. Let me share this also with you. Okay, please get familiar with these commands. Okay? I mean, don't panic. We will go through some of them, like create table is a command. What's the create table? What does the TTL mean? What does versions mean? What does block cache mean? We'll talk about it. Okay? These are the different...
Sorry to cut you. Would you like to forward us that one?
Oh, wonderful. Let's forward it.
Okay, thank you.
Wigio.com. I think we have to somehow, make this sort of comprehensive and crisp. List of all HBase commands.